We present MORALS, analysis of high-dimensional robot controllers via topological tools in a latent space. This is a joint collaboration between the CS and Math departments at Rutgers University. Our objective is to identify the regions of attraction, or RoAs, of desired and undesirable attractors of high-dimensional robot controllers without access to analytical models and given only a limited dataset of executed trajectories. Existing tools can be applied to low-dimensional systems like a pendulum, but cannot reliably estimate the RoAs for high-dimensional systems like a humanoid. Assume we are provided a dataset of trajectories of a tri-fingered robot hand pushing a cube to a desired pose. The controller is closed box. Estimating RoAs for such systems is critical for safe deployment of these controllers. This also allows us to compose multiple controllers with different RoAs into hybrid solutions. We will first recap our prior work on Morse Graphs, or MGs. Morse Graphs explain the global dynamics of a control system. That is, they identify all the attractors and their RoAs without access to an analytical model. In this illustrative example, we consider a one-dimensional dynamical system. This system has two attractors where it intersects with the y equals x line. First, we discretize the space and evaluate the dynamics locally at the resolution of the discretization. This lets us construct the combinatorial representation of the dynamics F. Collapsing all nodes that are part of strongly connected components in F into a single node gives rise to the condensation graph CG of F. We then obtain the Morse graph MG of F via identification of non-trivial strongly connected components of F. Finally, we can derive the RoAs from CG of F for the leaf nodes of MG of F. In this example, the nodes 1 and 2 of the MG correspond to attractors, and their corresponding RoAs can be identified in the condensation graph as AB and DE, respectively. We show the Morse Graphs framework applied to the phase space of an inverted pendulum using an LQR controller to stand upright. The Morse graph, shown on the left, recovers the central desired attractor 2 along with its corresponding RoA. It is able to do so only by evaluating the dynamics locally along a discretization. In addition, the Morse graph also recovers the undesirable attractors 0 and 4 as well as their corresponding RoAs. However, since the traditional Morse graph framework relies on a discretization of the state space, it becomes infeasible to directly apply it to high-dimensional robots. The proposed approach, MORALS, combines Morse graphs with unsupervised representation learning to study the RoAs for high-dimensional robots. First, it collects execution trajectories of the controller. These trajectories can then be decomposed into current state and next state pairs that are then used to train an auto-encoding neural network. Both the current and the next state are projected into a lower dimensional latent space by passing them through an encoder. The projected current state is then reconstructed back in the original high dimensional state space via a decoder. The L1 loss is a mean squared error between the true state and the reconstruction. To enforce the dynamics of the controller in this latent space, a latent dynamics network acts on the encoding of the current state to predict the next state's encoding. This is then fed back to the decoder, where the L2 loss minimizes the mean squared error relative to the true next state. An additional loss term, L3, minimizes the mean squared error between the predicted encoding of the next state and its true encoding. The architecture is trained end-to-end to minimize a weighted sum of these three loss functions in an unsupervised manner. Finally, MORALS performs a discretization of the learned latent space and constructs the MG that corresponds to the learned latent dynamics. We also prove that any RoAs for the obtained MG are also RoAs for the bistable Morse graph R of MG, which decomposes the dynamics into a single separatrix and a desired and undesirable attractor. This plot showcases the application of morals to obtain the RoAs of a 67-dimensional humanoid attempting to stand up. The latent space is two-dimensional, and the obtained Morse graph has identified two attractors shown in dark colors and their corresponding RoAs shown in light colors. To label the discovered attractors, Morals encodes all the final states in the training data. If the RoA of the considered attractor contains at least one successful encoded final state, it is labeled as a desired attractor. Thus, Morals can identify whether a new initial state will succeed or fail by encoding it and querying which attractor's RoA it belongs to. In these examples, Morals only sees the initial state and uses the MG to assign them to the RoA of the desired attractor. In these examples, Morals only sees the initial state and uses the MG to assign them to the RoA of the undesired attractor. Despite reasonable accuracy, Morals still suffers from some incorrect prediction due to learning error as shown here. To learn more, please visit our website and attend our presentation. Thank you.